Okay, 7-3. This time we're going to continue to use matrices, except this time we are going to be able to solve systems of linear equations using inverse matrices. Okay, now this is a very, very, very important slide here. Okay, a matrix equation takes the form AX equals B, where A and B are matrices whose entries are the coefficients of the system of equations. To solve for x, we must take A inverse and multiply by B. We will use our calculators to do this. So, we're going to solve a system using the inverse matrix. So, here we go. It's very simple. A is the coefficients of the left side. And the numbers go in just like you would think they would, just like they look like. Okay? And then matrix B is whatever's on the right side. So 0, 5. So X is going to equal A inverse times B. Okay? So when you enter these two matrices in, this is a 2 by 2, this is a 2 by 1, and you do A inverse times B, okay, you wind up getting a 2 by 1 matrix, okay, and the answers are 10 and sorry for the pause there, but apparently someone was trying to say something through my open window. It's kind of creepy. So anywho, all right. So the 10 represents X and the 15 represents Y. Okay? So that's very simply how you do it. The A matrix is are the coefficients on the left side, and the B matrix are the numbers on the right side. So if we have a system of 3 equations and 3 variables, no big deal. Okay? 3, -3, 6. I'm just going coefficients right here. 1, -3. I wrote my numbers too big. Get that down there. There we go. 10, and then -1, 3, -5. B is a 3 by 1 this time, and it's these numbers right here, 20, 40, and 30. So, A inverse times B, your calculators, and you wind up with 18, 39.3 repeating, and 14. So this would be X, Y, Z. And by the way, this just means the X matrix. It's the solution matrix, okay? So that capital X is that's the name of the matrix, that's all. So very simple. Now, if we wanted to determine A, B, and C so that these 3 points would be on the graph of f of x equals ax squared plus bx plus c. Now, here's what we would do. We could use a matrix to figure out what the coefficients of x squared, x, and the constant are. So here's what we do. We're going to wind up with a system of 3 equations. Check this out. So obviously this is the x and y coordinates. So we're going to plug -1. We're just going to look at this first point. We're going to plug -1 in for x. Okay? So a times -1 squared plus b times -1 plus c equals, the y coordinate is 5. So that's our first equation. Now we're going to take the second point. Plug in x. X is 2, so a times 2 squared, b times 2 plus c equals -1, because that's the y coordinate. Lastly, we're going to put in a third point. So a times 3 squared plus b times 3 plus c equals 13. Now we got to clean these up. So negative 1 squared is 1. So I've got A minus B plus C equals 5. 4A plus 2B plus C equals negative 1. And the third equation is 9A plus 3B plus C equals 13. So here's our system of three equations. Now instead of the variables being x, y, and z, they're a, b, and c. That doesn't change anything, okay? So when we do our matrix, our A matrix, 3 by 3, okay? So the first equation, the coefficients were 1, negative 1, and 1. Okay? So our second row is 4, 2, 1. And then 9, 3, 1. Our B matrix is 5, negative 1, 13. So our answer matrix, A inverse times B, okay? And again, I know I kind of glazed over this, but you're entering the matrices, you're naming them, you're doing the operations, just like we did in 7-2. You get 4, 6, and 5. That's your answer matrix. Now, what does that mean? That means that A is 4, B is 6, and C is 5. So your final answer is f of x equals 4x squared plus 6x plus 5. Because they wanted to know the coefficients for this quadratic, and we were able to use a matrix to find it. So this is strictly a calculator type exercise for you guys, and quite frankly 7-2 was as well. So that's how you can solve systems using matrices.